Good morning, champs. Today we connect statics and calculus. Until now, we handled distributed loads using geometry. Rectangles, triangles, and trapezoids gave us simple area formulas. But what if the load is not one of these simple shapes? What if the load intensity is a polynomial function of x? Then we use integration. The idea is the same as before. A distributed load is made of many tiny forces. At position x, the load intensity is W of x. A tiny strip has width dx, so the tiny force on that strip is dF equals W of x times dx. To find the total resultant force, we add all tiny forces. That means the resultant force equals the integral of W of x over the length of the beam. In other words, the resultant force is the area under the load curve. Now consider the example W of x equals 2 plus 0.5 x squared from 0 to 6 meters. To find the resultant force, we integrate from 0 to 6. The integral of 2 plus 0.5 x squared gives 2x plus 1/6 x cubed. Evaluating this from 0 to 6 gives 12 plus 36, so the resultant force is 48 kilonewtons. Next, we need the location of the resultant force. For this, we calculate the moment of the distributed load about the left end. A tiny force dF creates a tiny moment equal to x times dF. Since dF equals W of x dx, the tiny moment becomes x times W of x times dx. Therefore, the total moment equals the integral of x times W of x dx. For our polynomial load, this becomes the integral from 0 to 6 of x times 2 plus 0.5 x squared. Evaluating from 0 to 6 gives 36 plus 162. So the total moment is 198 kilonewton meters. Now we find the location. The total moment must equal the resultant force times its distance from the left end. Therefore, xr equals mr divided by fr. Substituting the values gives 198 divided by 48, which is approximately 4.13 meters. This result also makes physical sense. The load is much larger on the right side of the beam, so the equivalent force should act to the right of the middle. The middle of a 6-meter beam is 3 meters, and our resultant acts at about 4.13 meters. Good. The most important lesson is this. For any distributed load function, the resultant force is the integral of W of x, and the location comes from the first moment divided by the resultant force. Geometry formulas are just special cases. Calculus is the general method.